Okay, so we're back on the air. I hope you all had substantial coffee. Unfortunately, I don't drink coffee, so I'm not as awake as you might wish, but I will get back to where we were. Where were we? We weren't here. I'm sorry that somehow this got out of place. Here we are. Okay. So now I'd like to discuss about, so we've been talking about the logistics of setting up the problem, incoming wave, outgoing wave, and how do we define the quantities that allow us to then construct a cross-section. But we haven't said anything about the interaction. You know, what's actually, all the physics goes into this quantity that is, something happens when the nucleus, the projectile impinges on a target nucleus. There's an interaction that is going to cause the scattering effects that we will see when we measure, but we haven't really talked much about what this interaction looks like. And so I'd like to spend a little bit of time there, and then once we have an understanding of how to define that interaction, then we can move on to the applications. And so then I've asked Antonio to talk a little bit about the code that you'll be using to generate elastic scattering, to actually do what I said we need to do this morning about integrating this equation, matching asymptotic radius, extracting S matrices, and then constructing a scattering amplitude and a cross-section from them. So literally the code, you're not going to have to write the code is written, you're just going to use a code that does exactly what I described this morning. But first, as I said, I want to spend some time talking about the interaction. So if we need to start, I think it makes sense to start with the many-body problem because the target is a many-body problem. So let's think of a proton or a neutron impinging on your nucleus of choice, I don't know, oxygen 16, carbon 12, lead 208. You know, take your target. You've got a many-body problem. And so really the full system is really a many-body system with a many-body Hamiltonian. And so we'll start from this point. So consider then a wave function. I will call R0 the coordinate of the projectile relative to the center mass of this system, and R1 to A, the A nucleons of the target. Okay? And then we solve the problem, the Schrödinger equation in its usual way, but now of course there's particular boundary conditions that 1 to A are bound, but this last particle is going to suffer scattering. So there'd have to be some care if we really wanted to solve the problem as a many-body problem. Well, it's convenient to demonstrate what I'd like to demonstrate. It's convenient to split this Hamiltonian in a given fashion. So we'll pull out the kinetic energy associated with the projectile. We'll pull out the interaction of the projectile with all the nucleons of the target. Essentially, we're trying to separate everything that has to do with this projectile nucleon. And then we'll leave the rest in what we're going to call HA, okay? Which basically tells us how the nucleons inside evolve inside the target. So using this and this definition of HA, then of course I also have solutions for a Schrödinger equation that only involves the target nucleons, right? So I can write down, identically to this, a Schrödinger equation that only involves the target nucleons. And let's define phi I as being the complete set generated by the solutions of these equations. Now, one of them is going to be the ground state, which is the state that the target is in when I impinge the projectile on this target. All the others are going to be excited states. At least the ground state has to be bound for this to be a target, right? So otherwise it wouldn't be a target. So at least one is going to be bound and is going to have boundary conditions that are appropriate. But the whole set is complete, and so I can always expand the wave function for the n plus a, or the 1 plus a problem, in terms of this set. So let's write down the full wave function in terms of a sum of these phi j's times a chi that now is conveniently written as chi because it relates to my chi's that we talked about before. Now, the thing we need to realize is that we actually want to solve a problem where we consider the target is in the ground state. Okay, so we don't really at this point yet want to solve the problem that is more complicated. Let's assume that we can take just the ground state of the target. When we do that, that means we do a reduction of the model space. We know that in general our model space is bigger, but we're reducing it and projecting it onto the ground state of the target. That's basically what we want to do. So this means we have to introduce these projection operators that you may have come across before. So since at a starting point the target stays in the ground state, let's project the whole problem onto this ground state, defining a projection operator that projects onto phi 0, being phi 0 the ground state of the target. So remember what we defined as phi's are the many-body solution to the Hamiltonian of the target. So P psi picks up the ground state component of the target, right? Psi is the full problem, including the projectile, and when I apply P on psi, I get the ground state component, the part of the scattering solution that corresponds to the ground state component of the target. Now, properties of projection operators you've seen probably. I'm assuming that you know that P squared psi is equal to P psi. If you define Q as being the other part of the model space that you've left out, then this is also a projection operator that satisfies the same properties as projection operators. And because P is 1 minus, Q is 1 minus P, then PQ psi or QP psi are 0. They don't have any overlap. So now we apply these projection operators to our equation. So I haven't changed anything because P plus Q is 1. I've just put it in my equation. I've just said, well, my equation originally was E minus H psi equals 0. Now I've put in a unit operator in there. I haven't changed anything. Well, so there's going to be some algebra. There's going to be some algebra from this line to the next line, which I debated whether I should do it here or whether I should let you have a go. So I've decided you should have a go. And it's fun to play with these things, and I think you learn more than watching somebody else do it. I mean, that's basically what I come down to. Is once you actually do it, you're more likely to retain it. So after some algebra and manipulations, I mean, essentially what you're going to do is multiply on the left by P's or Q's and organize equations in such a way that you can get rid of some Q parts so that you get the projected part. You can come down to an equation that is written like this. So E minus T0, so the original equation, I'm not talking about the equation for the target, now I'm talking about the equation, the full equation, where you contain this equation, where R0 is included, where you are taking into account the relative motion between this extra nucleon and the target. So after that manipulation, and after integrating out the psi 0 part, you will get an equation that looks like this. Now, you look here, I mean, the way it's written at the moment, you've got a potential that is just the sum of the potentials of the nucleon that's outside, the projectile, and all the nucleons of the target. But you've got something else. So it's not only that, you've got something else, and that something else has to do with the stuff that you left out. It's the stuff in Q space, the stuff that is not in the ground state of the target. And if you look at the structure of this operator, this 1 over E minus QHQ, the structure of this operator can be written in expansion, if you expand over 1 over E, can be written in this way, and it's like multiple scattering of the effect of the Q space. So it's like it's taking into account the probability that this particle goes into the forbidden space, or the not included space, the Q space, comes back, goes in, comes back, goes in, comes back. It's like you can see it as a series of different orders of of multiple scattering of this particle into things that aren't target in the ground state, because our P space is target in the ground state. That's what we defined here as P space. So by looking at this equation, you can immediately see you can bunch terms in such a way and define an effective potential that is the sum of those two. Okay, you can define always some nu of R0 that is an effective potential that not only contains the sum of the two-body interactions averaged over the ground state of the target, but also some other more complicated term that takes into account the space that we haven't explicitly included in the model space. And that equation here should look now very familiar, right? We've been discussing that equation for 2 hours earlier, where it's just a scattering equation for this particle, this nucleon, sitting outside of the target. Does it make sense? So the thing that probably is not visible is the step from this equation to this equation, okay? And that step that might take a page, if you know where you're going, probably 1 page of algebra gets you there. It's not 10 pages for sure. That step is only manipulation of projection operators, okay? So now we've got this interaction. Now what? This interaction is basically an effective interaction between the projectile nucleon and the target, assuming that I can represent the effects of the Q space, the space that I've not included. So assuming the target stays in the ground state and I take into account the effects of the excluded space that wasn't included. So as I mentioned, the derivation of this effective potential is part of a homework that I would like you to work out. And in general, this interaction is not going to be local. So if you actually have a structure model that will provide this interaction, in general, this component in particular is not going to, maybe highly non-local. And what does this mean? So what this means is that your equation that I had written in a certain way can be rewritten in this way, where now you need to know the wave function in other points in space in order to calculate the wave function. So it's a little more complicated than what I described earlier. So, before I discussed equations that were local, right? In everything I said, I had a V of R that depended on 1 R, and I solved that equation by integrating out. I didn't have to know the wave function at R plus 5 Fermis to calculate the wave function at R. This is no longer the case when you have non-local interactions. So non-local interactions means the interaction has to know what's going on. Not only the wave function, in order to solve the equation. You need to know what's going on, not only at the r that you're calculating, but at a different r. That's why it's non-local. Now, we're going to avoid this complexity for the sake of what I'm going to discuss this week by making a local version of this. We're going to keep in mind that the many-body problem is more complicated than what we're making it. But for now, to start with, because we have to get started with something, we're not going to take into account this non-locality. We're going to somehow make a local version of this. And then we get what is called an optical potential. So typically, optical potentials are local, and they are obtained phenomenologically. They are fits to results, typically to data, to what you expect to obtain. If you've measured your elastic scattering, you've got an angular distribution. So that will constrain what this potential is. But the important point to understand here is that you got a stuff being scattered to Q space that may never return to your elastic. So what this picture of splitting into P and Q space, P being the ground state of the target, stuff that you've included explicitly in your description, and Q being everything else, that I'm not explicitly saying what it is, the fact that you've got this operator that takes this operator that scatters things into Q space, that means you're going to have flux that's never going to return back to elastic sometimes. So, very important feature of the optical potential is that it has to contain an imaginary term that accounts for the loss of flux into all these other Q spaces that we're taking into account. Now I'm going to introduce this term channel. We talk about channels. So the elastic channel is the channel in which target is in the ground state and you come in, if the projectile is composite, it is also in the ground state. Of course, the nucleon is in the ground state. That's our elastic channel. But you can think of many other things. You can think of excitation of the target. You can think of breakup. You can think of compound excited states. You can think of many other channels. The word channel for us will refer to the various possibilities of the Q space, okay, and the P space. Okay, so the important point to retain is that there will be a local simplification of this many-body effective interaction between a projectile and a target. That local simplification is usually phenomenologically based, but has to contain an imaginary term to account for flux lost into Q space. Make sense? Okay. Now, there's... Yes?
I don't understand, because if we make the hypothesis that target stay in the ground state, so we consider only the elastic scattering.
Mm-hmm.
But so why you speak about Q space may never return to elastics?
Because in reality... Okay. So we've built a model in what I've described and what Jeff started to discuss from the very first day. We've built a model that reduces this many-body problem to a two-body problem, and that assumes that even though these projectile and target may be composite, they are in the ground state. Okay? So this is our model. Reality is not like that. Okay? So what is happening in reality is much more complex, and it is a result of the many-body dynamics of the system. We are describing this in this simplified form, so we have to take into account the part of the model space we've left out. That's what I'm talking about here. It's in facing reality that we know, I mean, if reality was just the two blobs scattering from each other, two billiard ball type picture, then we'd be okay. but it is not, and we know it is not, and so we have to take into account the effect of what we're leaving out. And that's why that thing needs to have an imaginary term.
So the Q space take account inelastic scattering,
For example, it takes into account the effect of the inelastic channels on the elastic. Okay? So you are still calculating elastic scattering, right? Your observables that you construct are still going to be for elastic scattering. So what you need is the effect of all the other of the Q space on the elastic channel. Okay. We will probably tomorrow or the day after, we will talk about inelastic scattering. We'll talk about breakup. We'll talk about these other things that are related to Q space, and we'll include them explicitly and be able to calculate them. But what we're talking about today is how these other things affect the elastic. They are producing an effect in the elastic, and the most noticeable one is the fact that they're removing flux from the elastic. You're starting out with a certain amount of particles, and you end up with less because they end up somewhere else. Okay, it's this idea of unitary of the S matrix. The argument that I made that, you start out, the number that precedes the H minus has to be the same as the one that precedes the H plus because you can't lose flux. That goes away because if you have other channels that you can scatter to, then you lose from the elastic. So it's worth spending some time understanding the concept because once you start meddling with the code, you forget about these concepts. So it's good that we're spending some time thinking about it before you actually see how to calculate things. So we're going to use an optical potential that has an imaginary part, and that imaginary part is absorptive. It removes flux. It does not add flux. That would be unphysical. It removes flux. Okay, I was coming here and I was saying, how do you actually calculate this? Well, there's probably an infinite number of many-body models that you can use to generate these potentials. But let's just think of the simple folding of the nucleon. So you've got an NN interaction, so you've got a neutron or proton interacting with all the nucleons in the target, right? So that's what that sum refers to. It refers to the interaction of every nucleon with the target. It depends on R0I, which is the distance between this nucleon and every nucleon in the target. So it's going to change. It's not always the same R, right? Then you average over the ground state of the target. That depends on all the other coordinates. You get something that depends on R0, that is the distance between the center of mass of the target and this nucleon. Now, what is this interaction? Well, the first thing you can ask is it the free interaction? Is it the in-medium interaction? If it is the in-medium interaction, is it going to be density dependent? So probably, right? So if you've got a lead to a weight, it's likely that the interaction that it feels, especially if you're close, is going to depend on the in-medium interaction. So this thing already is not going to be a simple thing. And this is the radial shape for the volume term using, as an N, the Paris potential. So if you use given that we are in France, if we use the Paris potential and do that folding, you get something that's highly dependent on the energy and has a weird shape. It's not, not nice kind of Gaussian like we like, or Wood-Saxon. No, it's this. Now, I haven't really discussed it, but I can't really distinguish in my problem this proton from all the protons on the target, right? So there's this anti-symmetrization effect, if I think of it as a many-body problem, that has to be taken into account. And that's going to mess up this picture quite a lot when you take that. So typically people separate into direct and exchange, the direct being just this term, and then the one that has to do with when I do the anti-symmetrization properly. And so you get these two terms. And then one can look at what those terms look like in this simple folding model. I mean, the direct term is relatively straightforward to calculate, and people actually do this a lot. For example, I don't know if we might discuss JLM. We might discuss these folding procedures to determine an optical potential. It basically involves folding the T matrix for Nn with a density of the target. And so it's like a convolution integral that allows you to determine the optical potential. And here is an example of direct and exchange, and for energies around 100 MeV per nucleon, the exchange term can be quite large. So one can't just rely on the direct term. That's basically the point. Okay, so what we're going to do for now is not use microscopic theories to derive this optical potential, but rather use data. So we're going to say, I know that my potential is going to have to contain an imaginary part. It's going to have a central plus imaginary, a spin orbit. You know, like all of these systems, it's likely that there's going to be a spin orbit also. And so I'm going to try and fit parameters of an interaction to data in order to determine this effective interaction. Also, I'm making it local, right? Because keep in mind that in general it's non-local. So we have seen from experience that Wood-Saxon shape is a good description of the density of stable nuclei. And because there's no reason to assume that this effective interaction should go any different than the density distribution, we'll take also Wood-Saxon shape for the interaction. So the general form for the interaction would be 3 parameters for the real part and 3 parameters for the imaginary part. Depth, radius, and diffuseness, which define the Wood-Saxon potential fully. And a spin orbit that is defined in the usual way as a derivative term. I guess you've seen that already for the bound states. So it's all consistent with that. The radius is usually scaled by the mass in the standard form. And there are standard parameters for the depth. For the nucleon interaction and scattering at low energies, it's around 40 to 50 MeV. And for the diffuseness of stable nuclei, it's around 0.6. What number you actually get depends on your data set. Now, I was going to cover a few examples that Antonio then is going to discuss how we're going to do this in practice, in running the code. So let's take the case that Antonio has for the alpha on nickel. And if you do scattering at low energies, you don't really see the nuclear effects very much. Okay? So this is the process. It's purely Coulomb. It's well below the Coulomb barrier, and it goes pretty much like Coulomb. So this is a check when you run your little code to do scattering, single channel scattering. You can always lower the energy and make sure that at low energies below the Coulomb barrier, you get pure Coulomb. At some point, you're going to start getting these wiggles. If the energy is large enough that it's above the Coulomb barrier, then you get close enough to start seeing all the nuclear effects, and there's interference. The Coulomb is no longer the dominant thing. You get this diffraction pattern, and it's typically referred to as Fraunhofer scattering. There's an intermediate case in which Coulomb is strong, and you do get some pattern around this surface region, and you get strong absorption inside. So, you know, as soon as your impact parameter is small enough, you're going to absorb. There's a region in which things are going to happen, and then there's a region in which it's going to be pure Coulomb. And that's basically what you see over there. It's going to absorb, it's going to be Coulomb, and there's going to be a surface region where you're going to see some effects. And that's the Fresnel scattering. So I think, Antonio, I don't think we need to discuss more of the physics. I think probably I'll come back to tomorrow. We'll start again from here, and then we'll go beyond elastic scattering. But today, I think we should use the rest of the morning to discuss the various ingredients for the code that you'll be using this afternoon. So the homework problem this afternoon, apart from the two sort of analytic formulation type homeworks, you have one large section that has to do with actually solving your elastic scattering problem. You're going to choose a target, you're going to do proton on that target, and you're going to do several energies and try to understand what this optical potential is doing. What are the features of the optical potential that produce specific features of the cross-section and the angular distribution. So you're going to get a sense from this homework how elastic scattering works. But for that, you need to learn the tool. The tool is sort of a powerful tool that does a lot more than elastic scattering, and so the learning curve is a little steep, but I've been told that you guys are very keen, and so I have no doubts that you will succeed. And Antonio is really the best person to explain it.